Welcome. In this lecture, we are going to talk about fixed point implementation in embedded control system. So, in this lecture, we are going to consider digital platform for embedded control system implementation. Then, what is the binary representation for system representation, because any digital platform only accept binary data, either 0 or 1 digital data. So, we need to understand the binary system representation. Then, the fixed point implementation aspect in embedded platform, and finally, how to deal with sign number, sign binary number, and how can we correlate such sign binary number with an actual real world analog signal, which is quantized. So, in this case, we are talking about digital platform for embedded control system. So, if we consider any control system, whether it is a power converter or in typical consideration. So, we will have one which is called plant. So, this is like our plant, and it can be, in this case it can be simply our power converter. Then after the plant, suppose we have some output. So, we want to link that this output, in this case is the output voltage. So, this can be simply DC-DC converter or DC-DC converters. But it is not necessary, this embedded control system can be applied in many branch of engineering, but here we are considering DC-DC converter as a case study. Then we need to sense this voltage. So, how do you sense? So, generally there will be a sensor, okay, and this power converter. So, let us say sensor. If we are only talking about voltage sensor, then this sensor, that means voltage is very straightforward, we can sense, but in order to convert into digital signal, or in order to give this voltage to the ADC input, we need to go through certain stage. That means, we need to do step down, because it has to be mapped with the span of the ADC. So, this sensor, in case of DC-DC converter, typically has a resistive divider. So, that you can step down the voltage, so that you can comfortably take into the analog voltage span. Secondly, you may have to put some impedance matching network, so that the ADC will not be loaded. So, that means, some amount of signal conditioning circuit is needed, which can be the next step, that means, some signal conditioning circuit. So, this signal conditioning circuit actually include your buffer circuit for impedance matching and all, and it also include your A to D converter, ADC. That means, we have an ADC circuit. And so, this is a part of signal conditioning circuit, which is like ADC, because we are talking about the signal conditioning board, or even to be more precise, that means, if you want to. So, let us say this is just a buffer with low pass filter, it consists of low pass filter, because we need to reject some noise. Let us say we are separately considering ADC, that means, this will be ADC. So, here we should list one ADC in the list. This ADC, that means, the input to the ADC in analog signal. So, we need to make sure the signal conditioning output should match the span of the ADC. Now, this ADC data will be digital. So, it can be a number, it can be that ADC data. This number actually, if we consider this number goes to, this number goes to our feedback signal. That means, this is minus, and here we have some reference comment, which is positive. Then what we will have? We will have a digital controller. That means, we can have a digital controller. Then output of digital controller, in some cases we may need some DAC, and in some cases we may need actuator. So, it is an actuator. So, which is this actuator. Now, for power converter, actuator you can think like it is the gate drive circuit, that can be actuator, because you have to turn on and turn off the physical MOSFET switches. But you may not need DAC, because you are generating the gate signal. But suppose we will be talking about mixed signal current mode control, where you need to consider the DAC also. So, we will go to that point. But what I am trying to say, that up to this part, is in your digital platform, right. So, since it is a digital platform, this data which is going inside is a basically data. So, this data can be 8 bit depending upon whether we are talking about ADC. So, we have to consider what is the bit size of the ADC, bit size, is it 8 bit ADC, 9 bit ADC, 10 bit ADC. Then same thing is also applicable for DAC, DAC bit size, that means how many 12 bit DAC, 10 bit DAC, because input to the DAC and the output of the ADC, they are binary number. And so, we need to understand anything that we represent in the digital platform is basically a binary number. So, we have to understand some basic philosophical aspect of the binary number system, as well as how can we interpret such binary number into real world signal, because here the input to the ADC is an analog voltage. So, how it is mapped to the analog voltage, or suppose if we have an analog voltage, then if we pass through an A to D converter followed by a D to A converter, then we will get V A dash. So, it is a natural question whether V A dash will be exactly equal to V A, or there will be some effect of quantization, because this will have a finite word length 8 bit, 9 bit, it cannot be infinite bit, it will also have a finite word length. So, the actual analog signal has infinite resolution, but when it passes through ADC and DAC, it will have a finite resolution. So, naturally this V A dash will have some difference with V A in terms of quantization limit. So, that also we are going to consider. So, here in the binary system, when you are talking about the number that we are accepting as the input to the ADC, sorry, output of the ADC, that means we are talking about a analog to digital converter, we are going to see soon, and output of the ADC is a binary number. Now, this binary number, typically what comes out from the ADC, they are basically a line. That means, if we have an A to D converters, it depends, your analog voltage is there, this is the ADC. So, whenever you select ADC, you will have choice whether the data interface is serial or parallel. So, if you take a serial ADC, then it is just a one number, that means the number of the ADC, it is a serial ADC. So, naturally, if the 8 bit ADC, it is an 8 bit ADC. So, 8 bit will go serially. So, first it will start with a start bit, then it will have MSB, LSB depending upon the type of. So, it can be successive approximation, whatever ADC will use, but in case of serial ADC, we need to understand the data format, which data comes from, it is the MSB or LSB, then serially one by one data will come, and then once the data is over, then it is the start of the conversion. So, we should not mix the data of a particular corresponding to a particular sample with the data of the next sample. So, we should not mix up, we should separate it, but as you know that serial ADC has only one output wire or basically connection. So, naturally the data will come serially. So, the conversion process take times, but you can also have parallel ADC where the number of line can be parallel. So, you will get the data parallelly, that means it can be 8 bit, 10 bit, but here the number of data line will increase. So, as a result, when you talk about a digital platform, you need more number of pins of the digital circuit to accept that parallel data from the ADC. Okay. There is another possibility, because sometimes we can use an parallel ADC which can be high speed ADC, but suppose you have limitation in terms of IO pin of the digital device, then what you can do, because I am talking about, let us say this ADC data is going to a, let us say an FPGA that we are going to discuss. So, this data is coming, but suppose the FPGA does not have sufficient IO pin, because you are constrained in terms of cost, in terms of area. So, then what can you do? Your data output from the ADC is serial parallel ADC, because we want a fast ADC, typically serial ADCs are slow, but you do not have sufficient pin. So, you can use some kind of a interfacing digital circuit which can convert parallel to serial, and that will be a high speed circuit, because it does not need any conversion, it is just a codification. That means, you are converting a parallel data into serial, and it is a coding encoder and decoder that have to be linked, and by that way you can also manage, and this circuit can be very high speed, the encoder and decoder circuit that can operate at a very high frequency. So, you can, though there will be a delay of course, but still this delay will be much smaller than actual serial ADC. So, in summary, whatever ADC you take, whether it is a serial or parallel, these lines are basically a number, and depending upon the logic level, because now we are talking about CMOS logic, which can be 1.8 volt logic, in earlier it is to be 3.3, 2.5. So, it will only generate either high or low. When it is high, if the logic level is 1.8 volt, it will be 1.8 volt or it will be 0 volt. So, each wire will carry the voltage, which can be, we can take value from 0 or 1, which correspond to certain voltage. So, that means it is a binary number, but once it comes inside, then we can represent in different number system, either binary, hexadecimal, decimal, octal. Generally hexadecimal you can take 4 binary together, it is very easy, 0 to 16. Then octal 0 to 8, actually 0 to 7 it can create 3-bit number. So, these are the representation of a binary system when the data comes in inside a digital platform. Now, we are talking about a digital platform inside. So, we have n number of choice in terms of data, but in this lecture we are primarily dealing with this binary number and the decimal number, because decimals are very, because we all deal with decimal number 0 to 1, we are very familiar with the decimal number. So, sometimes we will use this decimal number to give you some kind of thought in the code, but we have to specify. By default Verilog take decimal, but if you want to specify binary, so you have to mention that is a binary. Now, out of this binary number that we are dealing with, since we will be dealing extensively binary number, the binary number can take different form. It can be straight binary, which is unsigned binary, you can say unsigned binary. That is typically we deal with unsigned binary, which is, let us say, if you take, let us say, lookup table, that means you are talking about B1, B0, B2. So, in the lookup table what we will take? We will take 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So, these are the 3 possibility, and this is straight binary, where it represents a number between 0 to 7. So, this is 7, this is 0. So, it is a 3-bit number. Now, this representation, there is no sign concept. So, it is just a number which varies between 0 to 7. But suppose the same 3-bit, that means it is a 3-bit unsigned number, 3-bit unsigned number, and which is represented by B2, B1, B0. This is the MSB and this is the LSB, that you know. Now, we want, that means B2, B1, B0. Now, we want to represent a signed number using 3-bit. How do that? Goes to one of the ways, the 2s complement, which deals with signed number. So, how do it is 2s complement? So, let me represent this B2, B0, that means you have bit which can take either 0 or 1, each of these bit can be either 0 or 1. So, what will be the number in unsigned number? That will be B2 into 2 to the power 2 plus B1 into 2 to the power 1 plus B0 into 2 to the power 0. So, this is an unsigned number which goes back to this straight binary. The same number, if I can use sign, then how does it look like in 2s complement? So, I am representing in 2s complement. So, this will be minus 1, then B2, everything else will remain same, B1 2 to the power 1 plus B0 2 to the power 0. That means, in 2s complement, so this goes back to our 2s complement. That means, if another is the offset binary. So, let us say we can have offset binary. Again, this is a representation where I will talk to you. So, I tell you, it is just you have to complement the MSB. That means, we will take it later. So, let us say in unsigned number, if all bits are 0, that means if we just rub up this particular table. So, let us say we have a number. Okay. So, let us say we have truth table which is B 2, B 0, B 1, B 0, okay, and we want to give unsigned number and signed number to the value. So, 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So, in case of unsigned number, this is 0. In case of signed, if you replace here all the bits 0, again it will be 0. So, both are same. When it is 1, unsigned number is 1, and you can see 2 leading bits are 0. So, this is also 1, there is no problem. 1 0, again it will be 2, it will be 2. 0 1 1, it will be 3, it will also be 3. But the difference comes when the MSB changes. When the MSB become 1, in case of unsigned number it is 4, but what will be the signed number? 1 all 0. So, this bit will be as if minus 1 into 2 to the power 2. So, it will be minus 4. So, this will be minus 4. Then what is the next? This will be 5, this will be minus 3. Then this will be 6, this will be minus 2, this will be 7, this will be minus 1. So, that means, here you can see the signed number can vary between minus 1 to 3. That means, what is the range of the signed number? The lowest is minus 4, highest is 3. In case of unsigned number, it varies between 0 to 7. So, what we will find that effectively the signed number in 2s complement, you can take a bipolar digit, that means from minus to plus, whereas sign, because in the A to D converter that we are dealing with, it will be sign, because we have to take the error voltage which will have a sign. So, that is why understanding this is important. Now, going to the offset. So, if you take an offset binary number, so the offset binary, in offset binary, in this case it is a 3-bit number. So, this will be simply whatever in 2s complement, right. So, you have to take the first, that means, I am just taking the offset number has 3 bit, it is 220, 3 bit. This will be equal to, you can say the 2s complement, that is the signed number, the complement of this MSB. That means, you are simply inverting, that means, whatever you will get this bit, whatever number you will get, it will be simply inverted, and then the rest of the bits. So, we will talk about the concatenation, it will be signed number 120. That means, in 2s complement, so that means, if we take signed number, so signed number starts from 0 to all 1, that means, in case of offset binary, what will happen? The offset binary, because in compared to the 2s complement, since you are inverting this particular data, right. So, we are inverting this data. So, we are inverting this data, the whole thing, this whole thing for 2s complement. So, in offset binary, all, that means 1 all 0 will be 0. That means, in case of offset binary, what will be the number? All 0, that means, it will be 1 all 0. That means, it will be just 1 all 0. So, that means, this number 1 all 0 will be the 0, and all 1 will be positive and all 0 will be negative, because in offset binary 1 all 0, in 2s complement it will be the maximum negative, okay. And all 1, that means, in offset binary, if you represent this 0 to 1, so it will from maximum to minimum. So, you can represent a negative bipolar number by suitably making the offset, that is why it is called offset binary. So, that means offset binary, in case of offset binary, this will be the maximum negative number. That means, it start with maximum negative number, this will be -4, then -3, because if you complement in 2s complement 1 all 0, that means 1 all 0 corresponds to -4. Okay. Then you will get the next digit 101, 101 will be -3. Then next will be 110, 110 will be -2. Then it will be 111, 111 will be -1. Then the next one, your complement is 0, 0, 0, it should be 0, then 1, then 2, then 3. So, that means, in offset binary all 0 will be -4 in this case and all 1 will be 3. So, it will vary from -4 to 3, and this is typically needed in our case, because you are using a D to A converter which has to be converted into offset binary. So, we need this thing. Okay. So, that means, in our case we need we need both this number decimal will be used in this representation. For ADC we will be using 2s complement. For DAC, whatever we are sending to the DAC digital data, that should be in the offset binary, because this comes from the data sheet of the manufacturer, and here we are using analog device ADC and DAC. So, we are making that data format according to their specification. So, example of binary number, that means, NX is a straight binary. So, you can represent. So, that means, if you represent, we have discussed, it is a 5-bit number. So, the first it will be B4, then B3, B2, B1, B0. So, B4 1, B3 1, B2 0, B1 1, B2 0. So, the number will be 26. What will be the maximum number? All 1. So, that means, 2 to the power 4 is 15, then 2 to the power 5 will be it will be 32. So, 31. Okay. So, the maximum number will be 31. Now, the next question. So, we have a data which is, let us say, 5-bit ADC. Now, this 5-bit ADC, it is in the form of straight binary, but because as per the data sheet, let us assume that this ADC is straight binary. That means, its number can vary between 0, that means, it can vary between 0 to 31. But we need to link how it is linked with the analog voltage, because it is dealing with a voltage. Let us say it is a single ended data. What is a single ended data? That means, it is a positive data. So, it can vary, let us say, between 0 to V span. In this case, let us say the span is 2 volt. So, it varies between 0 to 2 volt, which means 0 volt is mapped to the number 0 and 2 volt is mapped to the number 31. So, what will be the voltage for 1 volt? What will be the number? So, we need to map this data. That means, we need a scaling factor. So, how do we scale this number? So, whatever NX we are getting, if we want to convert into this, because now we are talking about a voltage, equivalent voltage, but you remember in analog whatever we are applying to the ADC, it is unquantized, that means it has an infinite resolution. But suppose if you think that I want to represent this data into an equivalent voltage, then there will be a quantized voltage. So, I would say that if this is your V A, then quantized V A, what will be that? So, it depends on the span of the ADC. This is that means the span divided by what? The 2 to the power bit, that is the number of ADC bit, this whole factor into your NX in this case. That means, if NX is 0, you see the quantized voltage is 0 because analog voltage is 0. But if the analog voltage is 2 volt, which is maximum, then we are getting Nx to be 31, that is the upper limit. Then what will be the quantized voltage? So, that means the quantized voltage for V A equal to 2 volt, this is analog voltage, will be equal to, what is the span? It is 2 volt divided by 2 to the power 5. 2 to the power 5 means 32 into the number will be maximum. So, Nx will be equal to 31. Okay. So, what will get? You will get 2 into 31 by 32, which is approximately equal to 2 volt, but it is less than 2 volt, it is not exactly. So, that means the quantized voltage level is different from the actual voltage level, and this difference will, that means the difference between the quantized voltage level minus or basically the actual voltage level, I would say this difference will, that we say the error voltage, this particular voltage, this error can be large if the bit size is small, because the resolution will be poor. If the bit size increases, then this error can be reduced. So, the bottom line is this, we have to be very careful about this quantization level, because if we use a very lower bit ADC, then the ADC cost will be smaller, the speed of the ADC can be also faster, or because this bit has to be processed for the digital processor. So, the processor width will also be smaller, because if you deal with a 5 bit data, then all the controller, all the filtering operation will be dealing with a 5 bit input data. But imagine if it is a 10 bit data, then you have to do all the arithmetic operation with 10 bits. So, naturally the size of the hardware architecture will increase, power consumption will increase, the propagation delay will increase, but the resolution will decrease, resolution will improve. So, that means it is a trade off between the accuracy and the power consumption or your computational time. So, you have to be very careful about the selection of ADC, because too large bit size can cause your hardware architecture cost too much, and that may not be acceptable. Okay. So, I think we understood the straight binary, that means this is the case example. So, this is in 2s complement. Now, suppose this signal, again this is an analog signal, this is an analog signal which varies between V min and V max. Let us say V min is minus 1 and V max is plus 1 volt. And again let us say it is a 5 bit number. So, now this 5 bit in 2s complement. So, the natural question, what is the Nx max in 2s complement? It will be 0 all 1. What will be the Nx min? Because we are talking about 2s complement, it will be 1 all 0. Okay. And what will be that? This corresponds to what? This corresponds to 15. And what will be this in 2s complement? This corresponds to minus 16. Why? Because we know minus 1 into, because this position is my B4, this position is B3, B2, B1, B0. So, this will be B4 into 2 to the power 4 plus B3 into 2 to the power 3 plus B2 into 2 to the power 2 plus B1 2 plus like 1 B0 2 to the power 0. So, if all bits, it is the leading bit is 1 all 0, that is the maximum negative or basically the minimum value. So, that means we can represent minus 16 number corresponds to minus 1 volt and plus 15 number. Now, you can ask me what is the resolution. So, the resolution, that means if I say delta V resolution, again it is the span of the ADC divided by 2 to the power the number of bit. So, in this case span is varying between minus 1 volt to plus 1 volt. So, it is a 2 volt span. And what is the bit size? It is 2 to the power 5. Then what is the resolution? So, resolution will be 1 by 2 to the power 4 volt, which is 1 by 16. That means 1 by 16, yeah. So, 16 volt, and which can be roughly around 0.0606 volt approximately, or something 0.06125 like that. So, what I am trying to mean, this is the resolution. So, there will be an error with the analog voltage, that means the quantized voltage level minus your quantized voltage level, this difference, if I take the minimum value of this difference, sorry, the maximum difference will be in the order of 60 millivolt. Minimum, if both matches, let us say if you take 0 volt, output is 0. So, then perfectly there is no error. So, typically the error can vary between plus minus. So, I am talking about the maximum magnitude of the error can be 60 millivolt, and sometimes this may not be acceptable, because if you talk about power converter with 1 volt output, then because of this quantization you may lose regulation up to 60 millivolt, which may not be acceptable. So, in that case we have to increase the ADC bit size, and that will define our, that means the ADC bit is defined by what is the resolution. But again this 60 millivolt is the raw data. Suppose we have an 1 volt output, then there is a step down like a resistive divider. So, it will further decrease, the resolution will further degrade, and we will discuss this aspect in the subsequent lecture. But the bottom line, we need to represent this binary number in 2s complement into an real world number, and that is why how can we link with this. That means, how can we realize this real world number? Again in this case will be your V span by 2 to the power n bit, this factor multiplied by n x, and n x can be minus to plus, and that is what we have represented. If this particular case, it gives rise to minus 6 volt. So, you can realize what will be the analog voltage for this case. So, what is the analog voltage in this case? It will be 2 by 2 to the power 5 into minus 6, and we know that this ratio is 60 millivolt. So, that means minus 6 into 60, that is millivolt. So, it corresponds to roughly 0.100 millivolt. Yeah, it is roughly equal to 100 millivolt. No. So, 1 volt roughly equal to, is it? $60 millivolt is the resolution, because it is okay. Let me write down again. 2 to the power 5 is 16. So, it is 2 by 32 into 6, which is 2 16, then 2 8 3. So, 3 by 8, sorry, it should be which means, yeah. So, which means for this particular case, it will become minus 3 by 8 volt. So, what will be that? Minus 3 into, so 0.125. That means minus, yeah, I think we are right. So, in it should be, there was a calculation mistake, it should be 0.375 support. Okay. Now, binary number. So, if it is offset binary A to D converter, then what will be the offset binary? Because offset binary means it is the I would say the complement of the MSB of the. So, that means, if this is, let us say we are talking about offset binary, which is represented by 0 1 0 1 0. So, we need to understand what is the sign value of this. This will be this bit has to be complemented. So, 1 1 0 1 0, which means minus 2 sorry minus 1 minus 1 into 2 to the power 5, then plus 1 into 2 to the power 4 plus 0 into 2 to the power 3 plus 1 into 2 to the power, oh, it is a 5 bit number, sorry. So, it should be, this will be 2 to the power 4, 2 to the power 3, 2 to the power 2, 2 to the power 2, 2 to the power 1 plus 0 into 2 to the power 0. So, this will be minus 2 to the power 4 means 16 plus 8, then plus 2, which is minus 6. That means, the same representation which we represented last time, in offset binary it will be minus 6, which corresponds to the voltage of minus 375 millivolt. If this, so this is a DAC, that means, if we pass a number in the offset binary form, it will result into minus 375 volt. Okay. So, that means, if we talk about this equivalent analog voltage, so we have discussed, if it is a 10 bit number, we can accordingly generate write down. So, first of all, we have to understand what is the span that we have discussed, that is a range of the voltage swing, which is compatible for that ADC. Then resolution of the ADC, we have discussed span of the ADC divided by 2 to the power number of bit. So, in this case, it is a 10 bit ADC. Then the quantized voltage level, whatever number we are getting, that multiplied by this factor that we have discussed. So, it will be quantized, and we have seen there is an error between quantized voltage and the actual analog voltage because of the finite resolution. So, then with this quantized voltage, for example, if we take the maximum voltage of an ADC is 2 volt, minimum 0. So, it is a single ended, only single unipolar input voltage. So, what will be the quantized voltage level for a quantized is 512 is a number, suppose it is a 10 bit ADC. So, 10 bit ADC means, that means so quantized voltage is what, for 512 2 to the power 10 is how much, 1024. Now, if we take Nx into 512, then what we will get? First of all, the resolution, that means Nx in decimal, it is 512 into what is the span, 2 divided by 2 to the power 10. So, it will be 512 into 2 divided by 1024. So, which is equal to 1 volt. So, that means the quantized voltage is 1 volt. So, in summary, we have discussed digital platform, some understanding of embedded control system implementation, number system of the binary. We have also discussed the fixed point implementation, and then we have also represent the sign number and how it can be linked with the quantized analog voltage if there is an A to D converter. So, that we can link with the real world voltage. Thank you very much.